Good afternoon, everybody. My name is Deep Pandey, and in our today's session, we will discuss a few details about network theorems. I hope you have a good idea about various network elements like capacitor, resistors, inductors, and so on. Right? So in our today's session, we will discuss like if we have different kinds of combination of these resistors or different type of combinations of inductors or something like that. So how can we solve such kind of combinations? Okay. So in order to solve these kind of combinations, we have different theorems, and these theorems are collectively called as network theorem. So I'm just listing out a few very prominent theorems. First one is superposition theorem. Okay. Then we have Thevenin's theorem. Okay. Then we have Norton's theorem. Then we have maximum power transfer theorem. Fine. And then we have Mellmann's theorem. Fine. So let me give you some brief details about all of them one by one. It's something like in terms of superposition theorem, this have like ability to separate the impact of each source on the quantity of interest. Okay. Similarly, about Thevenin's theorem, actually we can reduce any two-terminal series parallel network with any number of sources to a single voltage source and series resistor. And in the similar go, we have a Norton's theorem by which we can reduce any two-terminal series parallel network with any number of sources to a single current source and a parallel resistor. And after that, we have a maximum power transfer theorem, under which we can determine the maximum transfer power to a load to choose a load that will receive maximum power. And in the similar way, for Millman's theorem, we just check out for the power reduction. Now let us discuss some details about superposition theorem. Superposition theorem. Okay. So the superposition theorem is unquestionably one of the most powerful in this field. So by this theorem, on one hand, one can analyze networks that have two or more sources that are not in series or parallel. Okay, this may be a voltage source or current source or both of them actually. Similarly, next is like we can reveal the effect of each source, reveal the effect of each source on a particular quantity. Okay. Now, for the sources of different types, maybe it AC or DC, for the sources of different types, like it may be AC source or DC source, okay, and apply a separate analysis for each type, each type with the total result simply an algebraic sum of all the results of all these results. We will understand this with some example also. So let's move forward and take out the formal definition of this particular superposition theorem. It's something like, if we talk about the definition part, it's something like, let's say, the current through or voltage across, okay, like current through or voltage across any element of the network, any element of the network is equal to the algebraic sum of the current or voltage produced independently of each source of each. So current through a voltage across any element of the network is equal to the algebraic sum of current or voltage produced independently on each and every source here. Or in other words, this theorem allows us to find a solution for a current or voltage source using only one source at a time. And once we have the solution for each source, we can combine the result to obtain the total solution. Okay? Now, just keep this point in mind, and here we can go for some kind of applications. It's like first objective is like we have to remove the voltage source. Task 1, or you can say this in case of first objective, like remove a voltage source. Remove a voltage source. Under this condition, whenever we are removing a voltage source from a network schematic, we need to replace it with a direct or short circuit of 0 ohm. It should be short circuit. Okay? Any internal resistance associated with a source must remain in the network. Now let me show you some how it actually looks like if you replace one voltage source. Let's draw it. It's something like, let's say, um, if this is your network, okay, here this is, let's say, your resistance, some internal resistance, okay, and here this is your voltage source, like this, okay. So let's say this is some voltage V, and this is your internal resistance. Fine. So now if you have to replace this particular voltage source, how it should actually look like? It should be something like this way. And this. Okay. So this is your short circuit condition, and this internal resistance over here will remain here. Okay, this is how your circuit should look like. Fine. Once you remove a voltage source. On a similar go, if you are going to remove this current source, okay, while removing your current source, remove current source. Okay. In this case, what you need to do is like whenever you are going to remove a current source from a network schematic, you need to replace it with open circuit of infinite ohms. Okay. So any internal resistance here also associated with the source must remain in the network. Remember that for removing the voltage source, you need to put it in short circuit, and if you are putting it into, you are removing the current source, you need to put it in open circuit. Okay. Again, the shape is something like this. This point, let's say this is your circuit. This is your current source. Fine. And this is your internal resistance. Okay, current I is flowing from here. Fine. Now, if you replace, if you remove this current source, it should be replaced by the open circuit. Let me close it. Yeah. This is now open circuit, and here the internal resistance will remain same. It's something like this. Okay. So remember this point. That's a very important point over here. Like for removing a voltage source, it should be short circuit. For removing a current source, it should be open circuit. So since the effect of each source will be determined independently, the number of networks to be analyzed will be equal to the number of sources. It may be current source or voltage source. Okay. Moving ahead, it's like there are two different cases. Let's say for the case number one, let's talk about the case number one. Under the first case, let's say my requirement is, let's say this time particular current of a network is to be determined. Particular current of the network is to be determined. Okay. So particular network current is to be determined. What does it mean? It's like contribution to that current must be determined for each and every source here. So when the effect of each source has been determined, those currents in the same direction are added, and those having the opposite direction are subtracted. Okay? And so the algebraic sum is being determined. The total result is the direction of larger sum and the magnitude of the difference. Okay? Just like your vector addition, as you might have seen in your younger classes or in some other subjects also. Similarly, we have one more case, that is case number 2. It's something like a particular voltage of the network is to be determined. particular voltage of the network is to be determined. Okay, particular voltage of the network to be determined. That means like contribution to the voltage must be determined for each source. When the effect of each source has been determined, those voltages with the same polarity are added and those with the opposite polarity are subtracted. And the algebraic sum is being determined how this. And the total result has the polarity of the larger sum and the magnitude of the difference. Okay. Now moving ahead, let me take one very important aspect over here about the application of this particular superposition theorem. Remember that this superposition theorem cannot be applied to power effects because power is related to the square of the voltage across the resistor. Okay, or in other words, or current through the resistor. Okay, remember that. It should not be applied in terms of power because I'm sure you have idea like power is equal to I square RT, right? Similarly, it is like V square upon R, something like, right? So remember that. The squared term over here, squared term results in a non-linear relationship, okay, between your power and determining current and voltage. Power and determining current and voltage. Let me show this to you graphically actually. Let me draw the graph. See, in case of relationship between your current and power, it's like something. Let's say this is like P is equal to I square R T, right? This is the relation, and you can see here that this particular power is associated to the square of current, something like this, right? So if we can try to plot a graph between power and current, which showing the relationship between the power and current, you can see that this particular graph should be non-linear in nature, right? This is a kind of a square graph and it should be something like this way, right? It's obviously non-linear in nature here. Alright, I'm just showing it a negative part for this for your understanding only, like flowing in some different direction. So something like you can plot it also like this way, like this. If you can plot a positive current for this, this is how your non-linear characteristic. If I can put something like I over this direction, okay, and P on Y direction, something like this. Okay. So this is how it is showing you a non-linear relation here. That is the reason why we do not use it in terms of the power setup. Okay. So now let me do one thing. Let me show you some kind of application of this superposition theorem. Let me apply something on one of the circuit, and by this you will be able to understand it. So let's go ahead. Right. So let's say I have a circuit here. I'm just going to draw a small circuit, and we will try to apply this superposition theorem to solve this particular network circuit. Okay. So let me say the circuit is something like we have one power source. Here it is. Okay. Something like this. It is attached to one resistor. Okay. Over here, and one resistor over here. Fine. And attached to this, we have one current source. Something like this. Okay. And here we have, we have just connected it to ground. Okay. Now this voltage source or the voltage over here is, let's say, 36 volt. Right? This R1, this R1, and let's say this is equal to, let's make it around 12 ohm. Okay, like this. Fine. Similarly, R2, this is my R2. Let's say this is, let's put it 6 ohm. Fine. Then here it is a current source, and this is equal to, let's say, 9 ampere. Something like this. Fine. So now we have to solve this, and in the circuit we need to determine the current which is supposed to flow from this particular resistance, that is R2. Right? So obviously the current must be flowing from here is something like this way. Okay, and let's say this is like I2. Okay, I current is there, and we can make it like I2, and we have to calculate its value. Clear? So we have to find out like the current which is flowing through is I2. So here, first of all, let me try to solve it. Step number one. Step number one is, first of all, examine the effect of 36 volt. And for this, we need to replace the current source with open circuit. Examine the effect of 36 volt. Okay. So for this, we have to replace the current source. And I hope you remember, like if we are replacing a current source, so we must replace the same with open circuit. Okay. So let me redraw the circuit. What could be the circuit now? This is our voltage source. It will remain same. Then we have resistance R1. Okay. One sec. Something like this. Like this. here, and then we have like this, and okay, then this is the open circuit. Why? Because I have replaced this 9 ampere current source. Okay, and this time we have this as 36 volt. That will remain here. This R1, R1, which is like it will remain as a 12 ohm. Okay, and the R2 will be remain as your 6 ohm. Fine, this will be 6 ohm. Now what will happen? Some current should flow from here, right? It's like, let's say, this way. Okay, let me name this current as I1. First of all, this current will flow from, this time the same current will flow from this R1 and R1 and R2. So what will happen? Since these two, these two resistors are right now, there is no division of current. So in this case, these two resistors are actually connected in series, right? So what happens if these are connected in series? The total resistance over here, it will be 12 ohm plus 6 ohm, that is 18 ohm, right? And now you know very well using the Ohm's law, that is how you can calculate this current, that is V equal to IR, right? So I will be V upon R. That means I1 this time will become your 36 upon 18. 36 upon 18, and this will be your 2. The result will be 2 ampere. Okay, we have calculated the value of I1, and that I1 is now 2 ampere by this effect. Fine. Now, as a next step, what we need to do? As a next step, we are supposed to replace the current source, that is 9 ampere current source. Under the step number 2, we need to replace the current source. Or we can say, we have to replace the voltage source, sorry. Like we have to understand the effect of this 9 ampere current. We have to understand effect of 9 ampere current over the circuit. Fine. So the current source is to be replaced, is to have to replace this 36 volt, and you know very well that in order to replace a voltage source, what we have to do? We have to replace the voltage source using the short circuit. Okay, so let's make a short circuit over here. Let's make a small short circuit. It's something like our resistance will remain here. Okay, and this time it will be a kind of short circuit. It's something like this, and another R2 will remain in its position. Okay, and in a similar way, our current source will also be there, like this. Okay, then we have 9 ampere current source. Fine. Resistance is again 12 ohm. R2 is again 6 ohm. Okay. Now you can see here at this particular point, let me mark it in some other color so that you can have a clear distinction of this particular node. At this particular point, there is something called as current division is happening, right? One portion of current will flow from this branch and another portion of current will flow from this branch. Okay, let me mark it as I1 bar, and this let's mark it as I2, that we have already supposed from the very beginning of this example. Okay, I1 bar and I2. So now examine the effect of 9 ampere current. So actually what is happening here? These 12 ohm and 6 ohm resistors are in parallel. So what happens? Like how you can specify this? It's something like, let me write it for you over here. For this, the current that is flowing from 6 ohm resistor, that is I2, will be equal to, it's like R1 upon R1 plus R2, that is 12 divided by 18, okay, multiplied by 9. That is your total current. Well, so it should be equal to your 6 ampere. Fine. It should be equal to 6 ampere. So the I2 will be your 6 ampere. Fine. Now the thing is like what we have studied. Like we have seen that the 6 ampere is the contribution of our what? 6 ampere is the contribution of 9 ampere voltage source. Let me highlight it. This 6 ampere is the contribution of 9 ampere voltage source, and this 2 ampere, this is what your a result of your 36 volt voltage source. So we can combine both of them, and the final result will be your 6 ampere plus 2 ampere, and that will be the final result will be of 8 ampere. Right? We have to provide the algebraic sum. So it will be something like whatever I is equal to 2 ampere plus 6 ampere, and this result is 8 ampere. And this is your final answer. That is the current which is flowing through resistance R2. Final current. Okay? So this is how you can work on your superposition theorem. Fine. If you have any queries, any questions, any doubts, please feel free to let me know. You can type your comments in the comment box. Okay? And like you can let me know in case if you are interested for further studies on the same. Have a nice time ahead and take a very good care of yourself. Bye-bye.